The last class of macromolecules that we will cover are the lipids. The lipids are a bit different than either the proteins or the carbohydrates in that they are not polymers made up of repeated monomers. Nonetheless, they are exceedingly important and sometimes maliciously maligned. That is, fats have gotten a very bad name when we think about our diet, and in fact, as I ponder that, I ponder one of what has become my very closest, nearest, and dearest wonderful foods, and that is the avocado. And as it turns out, we need fats in our diet. They are absolutely essential to our diet. And a very good article that kind of surmises some of that is this one here. It was looking at the Hass avocado, which is the most common kind of avocado that we might consume. And it looks just at the nutritional facts for the avocado, but it ends by looking at the content of lipids, so fatty acids. And in fact, those lipids that we take in our diet are triacylglycerols. So when we talk quote unquote about fats, those are triacylglycerols. It's really cool to read through this because you'll notice that the avocado is packed full of dietary fiber, as well as some of the cofactors that we've been thinking about and vitamins that we've been thinking about and talking about in prior chapters. So ranging from vitamin C and vitamin A and vitamin K to niacin, remember the precursor metabolite to NAD, riboflavin, FAD. So these are all important in energy generation, but then it goes on to talk about the fact that it is 71% monounsaturated fatty acids, means that it's not saturated fatty acids that are in the avocado, but instead our monounsaturated oleate is actually one of those, and polyunsaturated, sometimes called PUFA, and we're going to learn about why these are so dang good for you. So I think many of you are going to be very interested by this. Perhaps Candace and Mandy and Amanda, I know for sure you will be, and it's really cool. One of the articles that has cited this actually talks about the way in which young people are not getting the nutrients that they need and instead are getting a lot of sugary foods, and so using the avocado as a possible age appropriate. And Landon might think about this too, right? I know you love kids as well. And so this is a food that could be supplemented in children's diet to help some of that nutritional deficiency. So we recognize that lipids are extremely important in our diet. One of the reasons for that is because they do help to comprise biological membranes. We will be talking, yes, of course, not only about the triacylglycerols, but also about phospholipids, quote unquote, learning why that's actually not a technical term, but we will be looking at the classes that comprise the informal grouping of phospholipids. We also recognize that they're extremely important in energy storage, so we can recognize that in multiple ways. Obviously, we know that fats are an anhydrous way to store energy, and so again, that is one of the reasons that they have been so maliciously maligned, is because they're such an efficient energy storage molecule. So the highly reduced hydrocarbon chains in fats can provide a great deal of energy, but they are anhydrous, they're water hating, so they don't take up they're not very weighty. And birds take great advantage of that. Actually, I've got a picture of a bird, and there were a number of you who mentioned that if you could be an animal, you'd want to be a bird. This is a bird that I encountered in Hawaii. And so when we think about the fats in birds, that as an energy storage molecule for them is exceedingly important, because they have to have something that's light in weight so that they can fly, but at the same time gives them long-term energy storage. While they're migrating, they need to be able to have a lightweight but very effective means of storing energy. So this is really important in birds. Also, if we think about the padding capacities of fats, we can also think about that in our marine life discussion. So going back to our first exam and thinking about how if you're a seal and you're trying to get away from an orca, you're going to really celebrate the padding capacities of your fat when you jump up onto an iceberg and try to escape getting eaten. So thermal insulation and padding. And not only are these important to other types of organisms, but to us as well. In fact, skiers, unless they have a certain level of fat, I've had some men skiers who have been below 3% or right around there, and they are very poor at thermal insulating, and we've had cases of hypothermia. They're also important in surface protection. So going back to our look at the bird, one of the classes of fats are waxes, and waxes coat the surface of the feathers of birds. So if you've ever watched a duck get out of the water and kind of the water bead up on the surface of its feathers, that's because of the waxes. So we will be talking about waxes. Recognize that they're also important in cell signaling and recognition. Another class of lipids that we will look at are the eicosanoids, and they're really important in regulating blood pressure, smooth muscle contraction, and whatnot. So these are extremely important. And we mentioned that, it's cliche, right? Fats don't go into water. The fats hate water. So they're very highly hydrophobic, insoluble in water. But they are soluble in organic solvents. So this is great for some of you who are incredibly interested in chemistry, and those who maybe have worked with lipids in the lab. We extract them with chloroform. So at one point I was actually trying to extract the lipids from a bacterium called Listeria. Some of you have heard of it. It caused that whole cantaloupe thing in 2011. But anyway, it was extracting lipids from that, and I used chloroform, a chloroform extraction, in order to do that. So as we dive into lipids, there are classifications. There are the isoprenoids, which are the steroids and lipid vitamins. There are the terpenes in plants that also fit into this category of isoprenoids. The more talked about group of lipids are the fatty acids, and we will momentarily be diving into the structure of the fatty acids. We will begin with the simple fatty acids and build from there. We will be talking about the triacylglycerols as a storage form of fatty acids, because in actuality, fatty acids themselves, they have a carboxyl polar head group and a long hydrocarbon side chain. They act like detergents. So a free fatty acid in the body, and some of you who study exercise phys know this, a free fatty acid in the body is very deleterious, very damaging. So in order to store them, they're stored as triacylglycerols, where there's that glycerol backbone is esterified to 3 long hydrocarbon side chains. Now, the next class will be the glycerol phospholipids. This primarily comprises the group that we know as the quote-unquote phospholipids, but there is one sphingolipid that has a phosphate group that would cause it to also be classified into the group that we are informally know as the phospholipids. So I'm just going to make note of that if you take the one group from the sphingolipids plus the glycerol phospholipids, this is the quote-unquote phospholipids. So, of course, recognizing, back to our avocados, that if you take in triacylglycerols, fats, in your diet that are amenable towards synthesis of good glycerol phospholipids, sphingolipids, and whatnot, then that can be very beneficial. So we're looking to try to get in a lot of polyunsaturated, and we'll look at the specific types of unsaturated fatty acids that as triacylglycerols you want to take in your diet. We talked briefly about the waxes and the very important signaling role of eicosanoids. So we'll jump into each one of those, but let's begin by just simply looking at the structure of a simple fatty acid, which is not so simple because that long hydrocarbon side chain can vary quite a lot. Now let's begin by looking at the carboxyl group of a fatty acid, and I want you to recognize that it is ionized, meaning that it has lost its acidic proton. Now this is going to make a ton of sense when I remind you that the pKa value of this carboxyl group is somewhere between 4.5 and 5. So when we think about that and we recall that the physiological pH of a cell is around 7.3 or 7.4, we recognize that this particular group, the pH, we have passed the pKa value. So the species that predominates at physiological pH will be the ionized species. That is, the predominant species will be the one that has lost its acidic proton. So when we look at that and frame it within the larger molecule itself, what we recognize is that it makes it so that the molecule has two regions. It actually literally has a polar head group and a long fatty acyl side chain, right? A long hydrophobic hydrocarbon side chain. Now, if you look at that, it's going to remind you of something that we recently have covered, and that is a detergent, right? It's got the polar head group and the long hydrophobic tail. So you might be thinking, wow, detergents, aren't detergents kind of bad for membranes? And you got it. If there's a lot of free fatty acids, sometimes we call them FFAs, free fatty acids, if there's a lot of those floating around within the cell, they can literally act as detergents, solubilizing membranes and literally wreaking havoc within a cell. Therefore, the concentration of free fatty acids is generally kept at a minimum to try to stop these deleterious effects. And we'll see in fact that structurally most fatty acids are stored at any given time as a larger molecule, a triacylglycerol, and that's what we know as storage and dietary fats. So let's take a moment to deconstruct the overall structure of a fatty acid, beginning first with the long hydrocarbon side chain. And I have a feeling this is going to be a super fun part because you'll recognize the hydrocarbon tail as something that nutritional facts tell us a lot about. For example, you may have looked at the label of some sort of food and noticed that it either does or doesn't contain saturated fats. What that refers to is the state of the hydrocarbon tail. So not only does the hydrocarbon tail vary in length, but it also varies depending upon the degree of unsaturation. So a saturated fat, meaning that all of the carbons are bound to hydrogens and there are no double bonds in the chain, versus an unsaturated fat where we see maybe more than one or more double bond that characterizes that side chain. And in a moment here, we'll look at a fat that is not saturated. So the picture that we're showing here, which actually is of laurate, the fatty acid named laurate, is actually a saturated hydrocarbon tail. It has no double bonds in that tail. Now, if we want to look further at the overarching structure of this fatty acid, we can cut it off at the next level up, which would be at the carbon of the acyl group here. And so that leaves us with what we term fittingly the fatty acyl side chain. So remember, we've talked so much about what an acyl group is. So essentially that idea of this being a C double bond O bond R, and that's what we're referring to when we look at this fatty acyl side chain. So essentially in a fatty acid, it means everything but the negatively charged or ionized oxygen. So the fatty acyl side chain is just the C double bond O bond R. We can then further speak about the whole fatty acid in its entirety as being that entire molecule that we see there, ranging from 12 to 20 carbons and almost always even in number. So when we talk about the whole fatty acid, that's when we're speaking about the numbers being even, and we tend to see those being more common, and that's literally because fats are generally synthesized 2 carbons at a time. We remember, maybe many of you remember, that it's synthesized from the precursor metabolite acetyl-CoA. So that makes sense that it would be built 2 carbons at a time, and we would see those being the most common. And in fact, if we look down below, you'll notice that some of the most common of the fatty acids are oleate, which has 18, palmitate, which has 16, stearate at 18, which stearate literally means from steers. It's a fat that comes from steers, palmitate from palm oil. So these are some of our most common fatty acids, and you might be noticing that palmitate and stearate, these are saturated fats. But now I want to turn our attention to a mono unsaturated fat, oleate. So notice that oleate is abbreviated as 18:1, and in a minute we'll talk about exactly what that means. But oleate is a mono unsaturated fatty acid, meaning that it has a double bond in its hydrocarbon tail, whereas palmitate and stearate do not have a double bond, and that's why they're abbreviated as 16:0 or 18:0, meaning they have 18 carbons in their chain, but none of them are double. There's 0 double bonds in that side chain. Now, before we leave this behind, I want to make sure to make reference to nomenclature and how we either number or name the carbons in a fatty acid. So we may either start with carbon 1, the carbonyl carbon of that carboxyl group, numbering down 1, 2, 3, 4, and so on down, or we may use a more common nomenclature where the first carbon attached to the carbonyl carbon is called the alpha carbon, and then alpha, beta, gamma, delta, epsilon, and so on down. But where things get a little bit confusing is with the terminal carbon. Always, always, always in a fatty acid, the last carbon is called the omega carbon. It doesn't matter whether it's stearate with 18 carbons or whether it's palmitate with 16 carbons. That final carbon in the chain is still called the omega carbon. And that's going to play a huge role in the nomenclature that we use for all of our fatty acids. So without further ado, let's take a moment to look at the difference between a saturated fat and a saturated fatty acid and an unsaturated fatty acid. Let's start with a monounsaturated fatty acid and then move our way into a polyunsaturated fatty acid that might have more than one double bond in the hydrocarbon side chain.
So fatty acids with no double bonds in their hydrocarbon chain, as we mentioned, are termed saturated. If a fatty acid has one double bond, and in fact if you look over here on the right at this fatty acid called oleate, this is got 1 degree of unsaturation. It's got 1 point of unsaturation between the 9th and the 10th carbon, and in fact oleate is the most common monounsaturated fat within mammals and most abundant. And what we see there is that it is, as we would call, monounsaturated, so 1 degree of unsaturation, 1 double bond. Now, if there were more than 1 double bond, and here in just a second we'll go ahead and look at the structure of a very, very famous polyunsaturated fatty acid that has more than 1 double bond. So polyunsaturated fatty acids, 2 or more double bonds in their side chain. Now looking just a little closer at oleate, oleate with its 1 degree of unsaturation can be given a sort of shorthand notation that is often used to relate the point of unsaturation and to tell where it occurs within the side chain. And we'll go ahead and write that shorthand notation down. What you do is you write the total number of carbons, which we see to be 18. So we start by writing the total number of carbons. You then write a colon, and then you write the number of double bonds. Then, in order to indicate where those double bonds occur, you put a delta and you write the carbon number of the first carbon involved in the double bond. That would be carbon number 9 in this case. So the shorthand notation then for this particular monounsaturated fatty acid with its cis double bond would be 18:1 delta 9. Now I hope most of you recognize this as being a cis double bond, and you're seeing of course then that both of our groups are on the same side of the plane of the double bond and both of the hydrogens. So this is what we would term a cis double bond. Now the other type of double bond, a trans double bond, has gotten quite a bad name.
So now something starts to make sense to you maybe a little bit too, because as I read on, I think, yeah, right here, trans fats have gotten a pretty bad name, haven't they? And so this one makes a point of saying trans fats 0 grams, and this one may do the exact same thing. Yep, trans fats 0 grams. So now doesn't that start to make a little more sense? Because here we see a cis double bond and not a trans double bond. Later when we're talking about some other types of lipids, we'll see some trans double bonds, and I'll bring your attention to that too at that point. But this one is a cis.
Over the past few years, there's been quite a buzz about trans fatty acids and how they shouldn't really be a part of our diet. Maybe you're wondering what trans fatty acids are and why they might have become sort of something that's the new talk of the town. Now, trans fatty acids do occur naturally in certain food sources, meats and dairies, but they occur in very, very low concentrations that are not a worry. But what does become a worry is the industrial production of trans fatty acids. So what is very attractive to industry is this idea of being able to make a product that has a soup's long shelf life, that is really, really stable for deep frying. It's only semi-solid, so it's like nice and spreadable, right? And so industry became very taken with this idea of making partially hydrogenated vegetable oils. And this is where the bad news came in, because that process of hydrogenation leads to the conversion from a cis double bond to a trans double bond. And in that conversion, we get the formation of a fatty acid that is much more highly implicated in cardiovascular disease. So notice in this image, we can see the typical cis double bond that we recognize from oleic acid or oleate, and we can contrast that to what happens when the process of partially hydrogenating vegetable oils takes place. This industrial process leads to this formation of trans double bonds. So while we know that unsaturated fats are better for us in our diet, and for many, many years the whole saturated fat is the bad guy kind of thing took hold, and that's what kind of led people away from butter, right? I mean, butter is a saturated fat, but it's a lot higher in saturated fat than margarines. But here's the clincher, is that when you do this process, this industrial process of hydrogenation, we form these trans double bonds, and guess what happens? Trans double bonds are far more highly implicated in cardiovascular disease. So this is I guess if you will, a bit of a catch-22. This is a fantastic article in the New England Journal of Medicine, and I would argue a pivotal one, because it was in the year of 2006 that the FDA said, hey, industry, you have to label your products saying that they have trans fatty acids in them, because guess what? This is causing cardiovascular disease. And so it was a sort of pivotal year for calling out the trans fatty acids. And so I suppose if I can find my soapbox in my office here, I'm going to say, you know what? Just give them all a little pat of butter. Eat butter. Go ahead and eat the natural stuff that has 2 things on the ingredient list, and stay away from these highly industrialized processes that create trans fatty acids, right? Everything in moderation, but everything natural in moderation.
That is one good-looking molecule. This is linolenate. Linolenate is, as we can see, as compared to oleate, it is a polyunsaturated fatty acid. Notice that it has 1, 2, 3 different double bonds. And in fact, if we want to, we can go ahead, and I want to, and write down the shorthand notation for this particular linolenate fatty acid. Let's go ahead and do that. Total number of carbons, 18. Ooh, that's exactly the same as it was for oleate. So 18 colon, what's next? Because now we have 3 double bonds, right? So 18 colon 3, delta, and now we have to pick out the locations of those double bonds. There is, like there was in oleate, there is one between carbons 9 and 10. So we have delta 9, but then we've got comma 12, comma 15. So 3 different double bonds, 3 degrees of unsaturation, and they occur between carbons 9 and 10, 12 and 11, and 15 and 16. Now this linolenate may not look familiar to you.
However, I'm guessing that it has begun to ring a bell with some of you, and I'll particularly call on Alexis because I know that she is a huge fan of Barbara Kingsolver, and I wanted to call to attention one of her best books, Animal Vegetable Miracle, And she speaks, and along with the writings of her husband and her kids, actually we'll talk a little bit about these fatty acids, and you don't necessarily know them by the names of linolenate and linoleate, but those are the two fatty acids that are absolutely essential in our diet. We don't have to take in any other type as long as we have those two. But again, you don't always know them by that name.
The more common name that it goes by is an omega-3 fatty acid. Gosh, the world is all abuzz about omega-3 fatty acids. Everybody's talking about them and how we're not getting enough of them in our diet. And of course then they tell you you better start eating more fish so you can get your omega-3s, but don't eat too much fish because you might get too much mercury. Yeah, it's a catch-22. But omega-3s are essential in the diet, and in fact we can get them from other meats, and I have to always step on my soapbox about that and say that we can even get them from eating beef, as long as that beef has been fed on grass. Okay, so looking then at what this means to be an omega-3, because how did that ever come up? Well, remember that in this common nomenclature for a fatty acid, we talk about the last carbon as being the omega carbon. If we then count backwards up from there, we see that the last double bond occurs 1, 2, 3 carbons away from the last omega carbon. So omega-3 means that 18 minus 15 is 3. An omega-3 fatty acid has the last double bond 3 carbons away from the omega, the terminal omega carbon. So they more often go by omega-3.
So we recognize that omega-3s and omega-6s are the two essential fatty acids in our diet. But this is problematized by the fact that most Americans get far more omega-6 than they do omega-3. So highly fried fatty foods in things like corn oil, maybe McDonald's French fries, are going to be much higher in omega-6s than omega-3s. In an ideal world, we would have a ratio of about 1:1 to maybe 5:1 omega-6 to omega-3. However, as this article states, we are not anywhere close to that in the average Western diet. So the average Western diet, individuals who follow that, have a ratio of closer to 15:1 or 16.7:1. So it's a very high omega-6 to omega-3 ratio. If that ratio is changed to being closer to 1:1, in this study 2.5:1, it reduces chances of colorectal cancer, breast cancer. It's less inflammatory. So I always talk to my ski team athletes when they're trying to recover from workout that they want to stay away from omega-6s and eat a diet rich in omega-3s. And I even encourage them towards plant-based omega-3s. And this is an article just really recently published, January 2016, looking at low omega-6 to omega-3, and this is just another nomenclature, N-6, N-3, PUFA, polyunsaturated fatty acids. This improves lipid metabolism, decreases inflammation, reduces oxidative stress, and increases endothelial function if omega-3s are a big part of the diet. So definitely seek out those omega-3 sources and stay a little bit away from those high omega-6 diets.